Snell's law, mu negative and mu epsilon negative concepts and absorption calculations, as I have seen from the uh, schedule of the workshop that for previous talks held from 27th July till today. So therefore, I will try to discuss about the thought process from the beginning of the equivalent circuit modeling and try to answer the questions that how to predict the equivalent circuits of the frequency selective surface for a particular shape. What are the operational regions on the basis of which the equivalent circuit modeling can be done, the key issues and the problems in predicting the lumped parameters in equivalent circuits. I will give some examples based on my work that how to think or to predict the equivalent circuit, and some examples of the metamaterials based absorbers related to its equivalent circuits. And finally, I conclude with some of the thumb rules of making the equivalent circuits for the frequency selective surface. Further, I also want to make this session interactive. Um, Please I request the participants to give me a privilege to ask 2-3 questions in between the discussions during my presentation, and all the participants are requested to answer the questions within 5 seconds in the chat window without opening the mic. So with these words, I just start with that. So as you know, why we want to work on the frequency selective surfaces, why we are so interested. As you know, there are many applications related to the metamaterials and frequency selective surfaces, like redomes, filters, antennas, absorbers, lens, clocking, subreflectors, reflector arrays, photovoltaic cells, imaging devices, and so on. So these are the basic, you can say, the applications, and many more applications are coming up with the using frequency selective surfaces and metamaterials that you have also seen from the previous presentations, that they are so important for us to do the studies in this field, basically. So with this, I firstly start with the basic definitions of the frequency selective surface. As you know, they are a periodic surface, which is an assembly of identical elements arranged in one or two dimensional infinite arrays, are generally known as frequency selective surface. Or you can say they are the periodic planar assembly of the metallic elements on the dielectric layer. Frequency selective surfaces can be cited in two ways, either the incident plane waves, or by connecting the individual generators to the every element of the array. Now, in the complementary FSS array, you know if the two complementary arrays are put on each other, a complete perfectly conducting plane can be obtained. The reflection coefficient for one of the arrays is always equals to the transmission coefficient of the complementary array. You can see the one reflection coefficient of, you can say, one surface will be equals to the diffusion coefficient of a complementary array. So now I'm directly moving towards the basic chronicle history of the equivalent circuit analysis. Why we want to do the equivalent circuit modeling. Equivalent circuit modeling allows the rapid computation of the frequency response of the designed structure. And moreover, it gives us the satisfaction as well as a verification which that the designed structure is correct. So it is one of the way of the verification of the designed structure. In some cases, if we doesn't able to measure or test our frequency selective surface, then the circuit modeling will be an alternative that the design structure will be is the correct one or not. The basic circuit modeling equations actually originally presented by Markowitz in 1951, and the equations that the Markowitz given is applied only for can be applied only for oblique angles of incidence component illuminated by E incident wave or a capacitive component which is incident by a transverse magnetic wave. So the second, then the work comes out from the model expansion method. The model expansion method comes in 1975, and it provides a comprehensive analysis. It gives you it gives the frequency and polarization responses at that time. It gives the physical understanding of the operation. It requires lengthy, but there are certain disadvantages also. It requires the lengthy computation time. So in 1975, it was just like a breakthrough that with the help of applying this method, you are able to, a designer or a researcher is able to give a complete, comprehensive, and a physical analysis of the design. But with the lengthy computation time, and it is generally not suitable for the complex elements, then due to these problems, another method comes in 1984, that is spectral domain. Provides the full wave analysis. And the equivalent circuit modeling technique was first applied to the frequency selective surface actually in 1975 by Anderson on self-resonant grids. I repeat, Anderson was the first person who has applied the equivalent circuit modeling to the frequency selective surface. So the equivalent circuit analysis is based on the basically equivalent representation of the frequency selective surfaces with series or shunt connections of the inductances and capacitances. And you, as you know, the classical numerical methods comes out thereafter, including finite difference time domain methods, finite element methods, integral equation methods, and method of moments. These are the methods that comes to equivalently define or equivalently represents the frequency selective surfaces. And these methods are basically, although they are computationally onerous and are dedicated, and they are other are, or you can say the integral equation methods and method of moments, basically. They are most famous methods due to their high efficiency, and which is used in conjunction with, both the methods are used in conjunction with each other, that is integral equation and method of moments. And averaging of the currents is one of the key which is discussed after these methods, for which is flowing in the periodic structure, or you can say it is an alternative way to drive the impedance of the metallic grid. So we will discuss this method in detail further. And more thing is there, generally students ask what is the basic difference between the frequency selective surface and metamaterials. Somebody is saying PPT is not visible. Sanjeev ji, is PPT is visible, not visible?
It's visible. I can see it.
Yes, sir, visible.
Okay. Okay. Thank you. Okay. So some participants, there are certain questions that how the frequency selective surfaces and metamaterials are different. One thing that I can say on this point is basically frequency selective surfaces are generally more concerned related to the filtering operation. Although logically, if you see, there are no difference, but if you uh, want to say it more specifically, they are more concerned related to the spatial filtering, frequency filtering applications. And metamaterial structures are related not only to simply restrict to the uh, filtering, but it has another physical mechanisms as well. So, further, in frequency selective surfaces, to consider the substrate effects if you want to have, then please remember these 2 points, that is second one and third one, that it will be good for us to grasp the concept thereafter. So to consider the substrate effects, the frequency selective surface capacitance needs to be multiplied by the average permittivity of the dielectric when periodicity is lesser than the operating wavelength or when dielectric is thicker than half of the periodicity. Please remember that will be an important concept to us. I repeat, frequency selective surface capacitance needs to be multiplied by the average permittivity of the dielectric if you want to consider the substrate effects. But this condition is only true when periodicity of the structure is lesser than the operating wavelength. Or you can say, or your dielectric is thicker than half of the periodicity. Then only you are able to consider the substrate effects by multiplying the capacitance with the average permittivity. Now, to move further, before moving further, there is a question for the participants, and I hope the participants will be able to answer it. Within 5 seconds, you have to put your answer in the chat window. So the question is this one. What is the condition for which a frequency selective periodic grid or structure with periodicity E, you can say, behaves as a homogeneous medium for the incoming or incident? Is anybody able to answer this question? I am waiting for the answer for this question.
20.
It is less than
Uh,
lambda g by 4. Periodicities must be lambda g
somebody,
by 4.
some is saying the periodicity should be lambda less than lambda by 4. No doubt, it is correct. Less than the operating wavelength. Somebody is saying less than lambda by 20. Actually, there are different views on that. But one thing I want to make it clear at this point is, let's say, firstly view the answer. If you talk about specifically, then the reasonable condition on which you can work, that the periodicity, if it is less than 0.5 lambda, then at certain point you can consider reasonably that it will be homogeneous. Or if you said generally, as some participants has also answered it, that the periodicity should be very much less than wavelength. So then it will be homogeneous. Means if this condition is not true, means if the periodicity is either equals to lambda by 2 or either nearly equals to lambda or greater than lambda, then naturally the equivalent circuit representation will be changed. So while deciding about the equivalent circuit representation, a researcher or a designer should keep these facts in mind, that while they are designing the circuits, so please keep this, that what is the relationship between the periodicity and the wavelength, so that the method can be chosen easily. So before now moving towards, somebody is saying the compactness is related to 0.02 lambda. So I have already said, please make a general view. Otherwise, it's very difficult to predict the equivalent circuit modeling, because equivalent circuit modeling concept is not like that. You see the circuit and just decide it over there. There are certain fundamental rules on the basis of which you can move further in designing the equivalent circuit model. So therefore, if you make a thumb rule that your periodicity should be as much as less than the lambda, that is sufficient for the homogeneous condition. So now I'm going to give you the basic key rules on the basis of which you can choose a method, on the basis of which you can apply the or you can apply your thought process, that on which direction we can move towards the, or what type of equivalent circuit modeling it can be. So a very important parameter in the frequency selective surface analysis is the wavelength at which the grating lobes are generally occurred. As you have seen in the previous year slides, as I have seen the presentation of Dr. Costa, that the wavelength at which the grating lobes are generally onset, that is equals to the D root epsilon r plus sine theta, where theta is the incident angle and epsilon is the permittivity of the substrate. That is the rule for the onsetting of the grating lobes or the trap lobes. That is for the embedded FSS. And if it is freestanding FSS, then the rule will be 1. Freestanding means when embedded FSS, when your frequency selective surface is embedded in between two dielectrics. And freestanding, when there is no dielectric waves, you can say, or there is, you have designed the frequency selective surface freestanding, or it is on some substrate like air. So in the analysis of this periodic structure, 3 different fundamental regions are classified. Please, you have to make these fundamental regions, you have to understand these fundamental regions very carefully if you want to design an equivalent circuit. The case 1 is if periodicity is very much less. This region is known as quasi-static region, and as we have discussed, the periodic surfaces can be efficiently analyzed using homogenized. So when your periodicity is very much less than the wavelength, then it will be better if you follow this theory while designing the equivalent circuit. And second one, if your periodicity is nearly equals to the wavelength or somewhat less than the wavelength, then it will be a better, or you can say the periodic surface element can be resonant frequency selective surface. And it can be modeled by circuit theory, and but the lump values you have to calculate using the full wave simulations in this case. And similarly, if you talk about the third case, when your periodicity is greater than wavelength, as I have told you, the grating lobe starts occurring, or trapped, it's also known as trapped mode region. And in that case, the frequency selective elements used to be represented or need to be represented using multi-mode. So that is a basic rules, basic fundamental reasons on the basis of which you are able to think that which technique I have to apply while I am designing the equivalent circuit. So we'll start with this FSS modeling, and with the basic equivalent circuit, as you can see, there is a wire structure, parallel wire structures, and if the electric field is parallel to the parallel wire structures, that is simply be an inductive component. And if there are gaps in between the wires, and then there will be the capacitance also there in series with the inductance. But if you say if the electric field is perpendicular to the wire, means in one case I am talking about the transverse electric wave incident, and second case I am talking about the transverse magnetic wave incident. In that case, if electric field is perpendicular to the wire, then it will be. Similarly, it means it will be a second rule. The first rule is the operating regions that we have already discussed. The second rule is you have to check that how the wave is incident on the structure. That is the another rule on the basis of which you can predict the equivalent circuit. Means, for example, as I have told you, if electric field is parallel to the wires, we can say that is an inductor. If it is perpendicular, then you have to say it is a capacitor. Right? So in that way, means the second scenario after the operating region, the second scenario is basically that the incident wave direction. That is very important in deciding the equivalent circuit. Now I will move towards in detail the discussion of the operating regions. So as we have seen, when the periodicity is very much less than the wavelength, then we have to apply the average technique. Average technique is nothing but it is why it is so called as the average. For simple non-resonant elements as wire grids or patch arrays, the impedance is mainly inductive or capacitive, as we have seen respectively. And one thing I also want to say, as we are saying the activity is very much less than lambda, so we are assuming the capacitive patch array, the patch array as a capacitive element. So the calculation of the inductance or the capacitance value can be accomplished by averaging the currents flowing on the periodic structure. So the derived FSS impedance is of the second order in this case. If you see, the impedance for transverse electric or transverse magnetic case, both the cases for the patch array, is given by 1 upon j omega c, where the value of the C patch for transverse for the. So that is what I want to say. The first condition is the operating region in which you are operating your frequency selective surface. The second thing is the direction of the incident wave. So depending upon the direction of the incident wave, we have to put this value of the capacitance over here. And if you see, you have the square terms over here. So this will be of the second order general. So that is a non-resonant. I repeat it again. That is when your periodicity is less than lambda, the structure is non-resonant. And if it is T wave, then the capacitance is different. If it is TM wave, capacitance is different. So next, similarly, in the averaging technique, if you have the mesh filter, then it is represented by inductance. And again, for the T incident wave, the inductance is different, and for the TM wave, the inductance is different. I request all of you, please. I have cited the detail. You can go for that references in which these concepts are given in more detail. So with the help of, by putting these value of the inductance for different for T or TM incident, we are able to calculate the impedance. So till now we have listened about, we have learned about the two rules. The first is the operating zone, and the second one is the direction of the incident waves for designing the equivalent circuit. Next is when the periodicity is either small, less than the lambda, or nearly equals to the lambda. So in this case, basically, when you are in this zone, so it is basically a resonant zone. So when your frequency selective surface comes in the resonant zone, so lumped components needs to be incorporated in the simple circuit model. Means what are the lumped components that needs to be incorporated? For considering the effects of the losses, a series resistance in the equivalent circuit of the FSS needs to be introduced. This is the series resistance. So that is why when your operating region change, so definitely equivalent circuit going to be changed. So a simple LC circuit can fit the frequency response of a capacitive frequency selective surface, whereas a shunt LC connection replaces the LC series for an inductive frequency selective surface, as you can see in the mesh filter. So by using the knowledge of the current density, the FSS reactance can be calculated on the FSS element in the first order retrieving method. That is the second method of depending upon the object. Using the classical transmission line theory, you are able to calculate the FSS impedance. In this case, you can see the FSS impedance calculation is different when your periodicity is less than the lambda in the first case, and it is the impedance calculation is different in this case. So that is the role of the operating region. So as you can see, the impedance depends upon the input reflection coefficient of the periodic structure, and this reflection coefficient of the periodic structure is basically depends upon the input reflection coefficient, which is this input reflection coefficient needs to be determined using full width simulation. So with the help of this, you are able to calculate the impedance. So that is the. Now in the same case, as you can see, once you have computed the frequency selective surface impedance at the two frequency points, these two frequency points can be arbitrary points. Arbitrary points means that it is possible to calculate the values of the capacitance and the inductance approximating the actual impedance by solving these two equations. And one more thing I want to say over here, if your frequency selective surface is embedded within the dielectric layers, then additional transmission lines is also be needs transmission lines representing the dielectric layers needs also be considered while retrieving the L and C values. Means here impedance of the frequency selective surface not only includes the resistance and inductance, it also be a capacitive effect when you are embedding the dielectric in between the when you are embedding the FSS in between the dielectrics. So at every step you have to think what type of structure you are using. So that is the third scenario. The first scenario is operating region. Second scenario is your direction of the incident wave, and the third one is basically the type of the structure or type of, or the, how you are placing your structure. On that basis, your equivalent circuit is changing. So by solving these two equations, we are able to calculate the capacitance as well as the inductance. So the two values of the impedance at the different frequencies can be calculated using full wave simulation for any two arbitrary frequencies, and if you solve then these two equations, you are able to calculate the values of inductance and capacitance. But this approach is somewhat unstable with respect to the chosen inversion frequency points, omega 1 and omega 2. These are the inversion points as arbitrary frequencies. They lead to some kind of inaccuracies in the calculations of the inductance and capacitance values. So to achieve the more accuracy, a basic thumb rule of calculating the FSS impedance, that is, if you are able to find out the null value, null point. Null point means the null point of the FSS impedance, basically. If you are able to find out the frequency at which the FSS impedance is going to be zero. Because if you find that frequency, that is directly in the relation between the capacitance and inductance, that is, capacitance is equal to 1 upon omega square to L. So at this frequency, you are able to directly evaluate if one is known. If you know the L, you are able to find out the capacitance. If you know the capacitance, you are able to find out the inductance with the help of the iterative processes. So that is the another way of approaching the accuracy at this point in first order retrieving point. Now the second question comes. Second question for all of you. You have to answer in 5 seconds. If one of the two adjacent dielectric regions supports a TEM field distribution, while the other supports a TE field distribution, then the common interface between the dielectric behaves as what? It is a question for the participant. If one of the two adjacent dielectric regions supports the TEM field distribution, then the and other supports a TE field distribution, then what will be the what the common interface, then how the common interface between the dielectric behaves? Anu Mohammed is saying it is capacitive. Any other? So it is another key point while deciding the equivalent circuit. Somebody is saying quasi. Kirti Anand is saying some quasi TEM mode. Any other? So let's see the answer. It is a combination of inductance and capacitance in series. So the answer is actually it is a magnetic ball. It behaves as a magnetic ball. Let's see the question again. If one of the two adjacent dielectric regions supports a TEM field distribution, if one dielectric, both are adjacent, and if it is TEM field distribution, let's say if it is an air, you can say, and other supports a TE field distribution, then the common interface is basically magnetic ball. So if you know such kind of concepts, you are able to draw the equivalent circuit very firmly. In magnetic world, generally magnetic field lines will be perpendicular to the interface and electric lines are parallel to the interface. We can modify the question as well. For example, in this case, if we say if one of the two adjacent dielectric regions supports a TM field distribution while the other supports a TM field, then what will be, then the common interface between the dielectric behaves as what? That is, can you answer? If instead of TE field, if I replace it by TM field distribution, which is generally, then it is electric wall. Nice, Divya Prakash. It's electric wall basically. And in that case, electric field lines will be perpendicular to the interface and magnetic field lines are parallel to the interface. In that case, if you know whether it is an electric wall or whether it is a magnetic wall, you can change your equivalent circuit accordingly. So there is Sometimes I feel very awkward when somebody asks that how we can see draw the equivalent circuit by just seeing the structure. There is no magic. There is no automation. Basically, it is the concepts. It is basically the physics behind it. So if you know that, then you are able to draw the equivalent circuits more accurately. Now, if somebody is writing about the reflection coefficient, we will discuss that also. So another very important point in the first order retrieving method is the cell periodicity and the dielectric effects. Why we so concerned about cell periodicity? Why we are describing or classifying the operational region based on the cell periodicity? Because if you scale all the geometrical dimensions of an FSS element, it gives you a shift in the resonance frequency. You can see because the complete size of the cell depends change the resonant frequency as well. So it is more convenient to element dimension not as absolute value but as to the element periodicity. That is why always the cell periodicity becomes the key factor in determining the operational region of the region of the frequency selective surface. Another important effect is dielectric. You have studied and discussed about the dielectric effects. Generally, we know that for the thick dielectric substrates, if there is a thick dielectric substrate on both the sides of the frequency selective surface, then resonant frequency is reduced by a factor equals to root of epsilon r, but by a factor of root of epsilon r plus 1 by 2 when the dielectric is present only on one side. So that is another point while designing an equivalent circuit. Another point is always we are discussing about the average permittivity or effective permittivity. The reason behind is for fixed relative permittivity of the substrate, the decrease of its thickness leads to a gradual shift in the FSS resonance towards the higher frequency. Means if your permittivity is fixed, then for a decrement in the thickness, here you observe a gradual shift in the FSS resonance towards higher value. So a good solution always is to study the effects of the permittivity as a function of the dielectric thickness. If you see the research papers or the literature that is discussed so far about the equivalent circuit modeling, you will find they have always studied the variation of the effective permittivity as with respect to the dielectric thickness. That is a key point. And that is why they have they have calculated the effective permittivity. And this is the formula to calculate the effective permittivity. Now we'll move further. The third method, that is when your periodicity is greater than the wavelength. In that case, it happens. The frequency selective surfaces are, if you want to that your frequency selective surface operates within the resonant zone and the grating lobe propagation zone, or you can say the trapped mode propagation zone in between the resonant, above the resonant, but less than the grating lobe propagation, then you need to have the two additional impedances are connected in series with the lump circuit. Means not only L and C or R is also there for accounting the losses, but two additional impedances to account for the higher order modes needs to be incorporated in the equivalent circuit with higher order impedances. And the values of the higher order impedances you can calculate with these formulas. I repeat it again. Please see the references that I am quoting where it is necessary in my presentation, so that you can discuss, you can study in more detail thereafter. So by somebody is asking what is the effect on the mathematics, we will discuss later on. So this additional impedances accounts for the higher order modes in these two values of the these are the two values of the impedance that your FSS needs to operate above resonance zone, but just before the trapped mode, or just at the edge of the trapped mode, where the trapped modes are generally onset. Then to account the higher to consider these two impedances. So that is the fourth thumb rule. I repeat, first thumb rule is your periodicity. The second thumb rule is basically, do you remember what is the second rule? Anybody? What is the second rule we have discussed?
Incident wave
For
direction.
drawing incident wave direction. That is the direction of the incident wave. So first is periodicity, second is incident wave direction, third is, you can say, what is the third one? Anybody? The third one. We have discussed about the third one. That
Periodicity.
is substrate types, basically. Where you are placement of your frequency selective surface, where you are placing it, above the wish dielectric or in between the dielectric. And the fourth one is basically the zone. If you are just want to onset where you want to operate, that is means the fourth one, if you want to operate at the grating lobe onset, or if you want to want to propagate the higher order.
The operating region.
Yes, is somebody saying something? So these values you can see there, we are using the input impedance and TM input impedance that can be calculated by using these two formulas, and the further the complete value can be evaluated with these formulas that you will find in the reference. So that is again for TE polarization and TM polarization. These are the formulas to calculate the number, and you can use put these values of the wave number here, and then able to find out the value of ZC, and you can put these values of ZC over here to calculate ZB, which can be put over here to calculate Z in input, and then the values can be put over here to calculate the inductive and capacitive impedances of the value of Zn and Zc. So another, as I hope so, somebody is also asking this question, using the conventional, when you talk about the generic FSS system or frequency response. Generic FSS system, now some participant is also discussed how we can calculate the reflection coefficient of this. Using the conventional transmission line, the approximate reflection and transmission coefficients of the FSS can be evaluated by using these formulas. And here you can apply the transmission matrix, ABCD matrix you can use, and the values of the ABCD matrix is nothing but that is the multiplication of these matrices from which you have you can calculate these matrices from this value, and these are the formulas reference 8, and as I have shown you, this is the reference, so you can use this reference to find out these formulas to calculate the test. So next question for you is a half wavelength long short circuited transmission lines. How it behaves? A half wavelength long short circuited line transmission line. How it behaves? I think actually due to this slide show, all are asking the capacitive value or capacitive reactance, so it's correct. The reason is that when you design some kind of microstrip structures, for example, if you design a microstrip based frequency selective circuits, then this concept really helps you, because for example, if I said, let's say, let me change the question. For example, if you have a quarter wave long open circuit transmission line, then how it behaves? A quarter wave open circuited line. Sneha Shah is saying it is L. Somebody else, this inductive Siddhant is saying capacitive. So let me answer this. If it is a quarter wave long open circuited line, it behaves as inductive. And so it is better always, while you are going for drawing the equivalent circuit modeling of a transmission of a frequency selective circuit or any microstrip structure, you please read the transmission line here. You have to be very much clear about the concept of the transmission line theory, the short circuited transmission line or open circuit transmission line behaves. It will really help you to decide the component which component will be incorporated in the equivalent circuit. So now we'll move towards some of the good work in frequency selective surface of or basic shapes of the frequency selective surface, that how we can calculate these values. So as you can see, it's a square loop frequency selective surface, which is designed on the dielectric, and the square loop, simple square loop is basically equivalent to the shunt connection of series LC network, and the substrate is represented by this network. The values of the substrate inductance and capacitance you can calculate simply by applying these formulas, that is mu naught mu r mu h for inductance and for capacitance epsilon naught epsilon r h by 2. So these are these two simple formulas with the help of which you can calculate the value of the substrate parameters. And I'm going to discuss you a very important concept related to increasing the bandwidth by using the frequency selective surface elements and with their equivalent circuit model. So it is a square loop element which is designed, and the simulated frequency, as you can see, transmission response comes at 7.7 gigahertz, and the calculated value is at 8.05 gigahertz. How we have calculated, and percentage error comes out to be that is 4.3, and the square loop values of inductance and capacitance comes out to be 1.57 nanohenry and 0.12 picofarad by using these two formulas. And for substrate parameters, so for substrate parameter it is 1.27 nanohenry and 0.95 picofarad. That is for the substrate. And the square loop values are calculated how we have evaluated the square loop. So we'll discuss it. So the second, let's say, as you can see in the previous slide, it is the square loop and it gives the peak over here. So in order to enhance the bandwidth, we have taken the another element, that is JCS, Jerusalem cross slot element, and its standard equivalent circuit is consists of the shunt connection of the two series connected LC network, and the basic concept of why this is LC network you can see over here, depending upon the dimension of the Jerusalem cross central part. It is an inductive element, and the gap between the two adjacent elements gives you the capacitance, so that is why it is LC network. So this is a designed Jerusalem cross element, and these are its calculated value. How these are calculated, we will discuss it. So by using these two elements, one is the square element and second one is the JCS element. This is the response of the JCS element. You can say the peak is at nearly 12.7 in simulation, and in calculation is at 12.5. So by using the two elements, square loop and the JCS element, in combination, if you see over here, if we combine these two elements, then we are able to increase the bandwidth by combining them. So we have done that actually. So you can see over here, that is a basic combination in which we have combined the square loop and the JCS, and you can see over here we have got a very good transmission bandwidth. So and the frequency we about 11.89. So it is then we have modified it or optimized it, and you can see over here. So pad points and pad points of GCS are also incorporated, and the bandwidth increases to 15.22 gigahertz. So that is the final combination, final optimized design. No, it is not on the other side. It is on the same side. It is on the same side, sir. Somebody is asking about this. The square loop and the JCS is. Please show the slide number 31. Okay. So you can see over here. So it is 14.72 gigahertz band. So if we combine the two, we are able to calculate the increase the bandwidth definitely, and this is the final optimal design. In which we have so in this way, with the help of the equivalent circuit, you can say we have drawn the equivalent circuit of the JCS as well as the equivalent circuit of the FSS layer, and we have calculated it, we have optimized it, and able to get the very high in this case. So this is the FSS under normal incidence. The response of that FSS square loop and JCS combined, you can see here the bandwidth is 15.87 gigahertz. And these are the optimized stages. You can see in stage 1 there is only a single square loop. In stage 2 we have combined across with the square loop. We get the bandwidth. In stage 3 we have little bit increased the pads, and in stage 4 we have parallel optimized configuration, with the help of which we are able to get 15.87 gigahertz of equivalent circuit as well as simulation as well as optimization. So that is will be done. This is done with the help of the streamlined planned structure. So you can see over here the bandwidth increment by different stages using square loop combination, square loop with JCS, and final optimization. So next structure, that is another one. It's also an example. Is again a wide stop frequency selective surface. This is about the technical analysis also. You can see over here. This is nothing but it's a square loop, symmetrically on the four sides of the stop band FSS. And you can see over here, if the slots are not there, means for a conventional loop, you will get this transmission response. And when you cut over here, you will get this transmission response, but the bandwidth is higher. And you can see over here the transmission bandwidth even less than minus 20 dB is 7.7 gigahertz, and periodicity is of the order of 0.33 lambda naught. And the basic equivalent circuit model is this one. You can see these formulas. These formulas are somewhat different. I request you to go for the study the references for designing such network or designing the equivalent circuit modeling for such networks. As you can see, this represents the dielectric effects, and LNC represents the FSS effects. And in this case, the FSS is on both sides, not on the single side. The FSS is on both sides. So these are the formulas on the with the help of which, that is the substrate values, that is, these are the same as we have discussed previously, and these are the key formulas with the help of which this equivalent circuit model is solved. And the design stages, or you can say equivalent circuit modeling optimization. Sir, we will discuss the equivalent circuit. Sir, angular stability is definitely good if a structure is homogeneous. As I have shown you, that the periodicity is 0.33 lambda naught. You can see the periodicity is even less than lambda by 2. So definitely it will be a good angularly stable structure. So the second with using this formula, the another key important thing, that another key factor in this is that will be a very important. If you see in the design over here, there are two peaks. You are able to see over here. So the first peak calculation can be done with the basic equations. These equations are with the help of these equations, they are able to calculate the first peak or transmission peak. But for the second transmission peak, we have developed our own method by using the curve fitting technique. We have derived the formulas. That is, this is the first resonant frequency is simple. That is 1/2 pi LC formula. You can see over here that is dielectric and FSS capacitances are there, and you are able to calculate the first frequency. But for the second frequency, we have you are able to see this is not a regular formula. The formula is designed using the curve fitting. So that is the fifth rule of the equivalent circuit modeling that I want to tell you. That sometimes it comes in a situation with the circuit that how the equivalent circuit modeling will be verified. So in that case, you have to find out some math. You have to go for some mathematical techniques and the optimizational techniques. So this is basically a equation which is being drawn with the help of these three equations, where the value of a and b is also evaluated using these tables. You can see over here we have calculated the simulated as well as we have evaluated the simulated as well as calculated values of the second resonant peak for different values of the W, W1 and L1. What are the W, W1, L1? You see, this is W, this is W1, this is L1. So the fifth point that I want to tell you, that the constitutive parameters of the structure. So constitutive parameter structures, constitutive parameters, you need to understand that what are those parameters on which a particular behavior or particular response comes out in a FSS or in a metamaterial structure. So if you able to find out that these are the particular parameters of my structure, which with the help on which this type of response depends, then by optimizing or then by optimizing only those parameters, you are able to draw the equivalent circuit. Means, as you can see, I have calculated only for the three values, that is W, W1, L1. So first of all, I have to understand that how I have chosen these parameters. That is not shown in the presentation, but I make you clear that I have studied the variation of the width L1 and variation of this width with respect to the second peak. And observed that the first peak remains almost fixed and the second peak changes by changing these three parameters. So that means that clearly shows that these three peaks are these three parameters are basically or the value of this second peak depends upon these three parameters. So with the help of these three parameters, I'm able to derive this equation and retrieve the value of the second frequency. So that is the another method of retrieving the your equivalent circuit parameters. So that is the fifth point. Next, I'll move towards the third structure, that is double square. Generally, most of the participants are more focused on the double square. So, although there are many research articles are there on double square loop or triple square loop, but I'm giving you the study of the double square loop based on the equivalent circuit analysis. So, in this, as you can see, we have the two transmission peaks over here corresponding to the double square loop. But when we talk about the equivalent circuit, these are the equations, and these are the table shows the complete calculated values of each and every parameter of the equivalent circuit. That is the equivalent circuit of the double square, that is L2, C2, L1, C1. But these are the equations, with the help of which you are able to calculate every parameter's inductance, capacitance, susceptance, reactance as well. And when you calculate this, simply by applying the frequency formula, you are able to calculate the frequencies, both the frequencies. That is, you can see the first is at nearly 4.88 and the second peak is at 9.39 in simulation, and in calculation you can see it is at 4.56 and 9.35. That is quite close to each other. So that also gives us the idea that the drawn equivalent circuit and retrieval process is correct. So that is the another value, that is the standard formulas with the help of which you are able to. Next, I'm going towards the high impedance surfaces. High impedance surface is the another concept that is comes in 2000, that is discussed in more detail by at first in 2009. that how the bandwidth calculation using the equivalent circuit can be done. Till now, we are only retrieving the inductance value, capacitance value, frequency values, but the bandwidth calculation using equivalent circuit model. So the conventional approach generally for the high impedance surface, if you use the high impedance surface for a limited region, it is also known as artificial magnetic conductor, limited for a limited frequency range. So conventional approach which describes this high impedance surface as a basically a parallel connection between the inductance and the capacitance of the FSS. Inductance of the grounded substrate and capacitance for the FSS that is connected. That there will be a parallel connection between the two. But after this work, it came to the picture that an inductance which drives this inductance needs to be incorporated if we want to calculate the bandwidth correctly, if we want to achieve the accuracy in the band. The high impedance condition is verified when the denominator of this impedance is null, and you can say it is namely the angular resonance frequency, and the bandwidth of a high impedance surface is basically defined as the frequency range where the absolute value of the impedance, you can see over here, eta, this is basically representing the free space impedance. So the bandwidth of a high impedance surface is defined as the frequency range where the absolute value of the impedance is larger than the free space impedance. You can see over here when the absolute value is just larger. So from this point to this point, this is the range. That is the high impedance surface bandwidth. And one more thing I want to clear over here, while you are dealing with the high impedance surface, not only the bandwidth, you can choose the your surface in such a way that what type of characteristics you want, you can change the surface accordingly. So on that basis, equivalent circuit will going to be changed. So that is why this series inductance of the FSS has been introduced, and that is and it that will help to properly evaluate the bandwidth of the high impedance structure, and that is why it is a complete circuit for a high impedance surface. So that you can say 6 points that I'm going to tell you while you are dealing with such kind of surfaces for equivalent circuit analysis. Now, another question for all of you, it's a very important question. The resistance of a simple carbon composition based or a metal based resistor. How it behaves if it is used at radio frequency or microwave frequency. What can be the how the resistance can be represented if you use a simple resistor, carbon resistor or a metal resistor at RF frequency or microwave frequency? Can you add? Any of the participant inductive? A very high resistance, somebody saying it is inductive. Somebody saying inductor. Somebody else, it is a low resistance. Somebody says losses increases. Okay, for inductive, Manish Sharma is saying inductive. Gokulan saying Niranjan is saying inductive. So the resistance of the let's see the answer first. Sony Devi saying. So let's see the answer first. So answer is it decreases. I'm not asking about the increase. Please see over here. Somebody says the resonant, definitely a resonant, it becomes resonant. The resistance of a simple carbon resist composition, it will decreases if it is used at microwave frequencies. Your resistance decreases because at simple DC frequency, it is simply a resistor. But when you are using at RF, in effect increases. When skin effect increases, then uh, another inductance comes out and a resistance comes. And one more thing, this resistance is greater than this R value, so it becomes lossy, as somebody also says, lossy. So please keep these things also in mind while you are dealing with active kind of frequency selective surfaces, that what kind of chip resistors you are using, what chip your surface mount devices you are using in your tip surface. So while designing the equivalent circuit modeling, please keep in mind that while you use such kind of devices, either chip resistance, etc., then overall resistance going to be decreased and your equivalent circuit going to be changed. So next, another very important work that comes out in 2013, that is wire-based metamaterial absorber. Now we'll move towards the equivalent circuit modeling of the metamaterial absorbers. So the basic concepts of the metamaterial absorber, you already know that how absorption is going to be calculated, how the reflection coefficient or transmission coefficient behaves. You have already covered in your previous lectures. So I'm directly moving towards the equivalent circuit modeling of the wire-based metamaterial absorber. Metamaterial absorber. Uh, the author basically, or the researcher actually said that the wire, as you can see, is of metal having the dimensions width W and length L, then it will be considered as a cavity modeling, as you can see. And the basic aim of considering the cavity modeling is to derive the equivalent circuit model to investigate the influence of constitutive parameters on the absorption. That how the constitutive parameters, how L, how W, how D affects the absorption level, not only the not only the absorption frequency, but absorption level as well. So it is a cavity model basically, and as you can see in the cavity model, uh, the they have considered that absorption frequencies that there is the main mechanism in this kind of structure is the magnetic resonance. Um, each wire and plate pair can be considered as a cavity-like resonance and modeled as a parallel LC circuit. As you know, it's a cavity structure, so it is a parallel LC circuit basically, and inductance is associated with the parallel wire plate pairs, or you can say the grounded dielectric substrate, and capacitance is created due to the gap between the wire and the bottom side. So it is the another way of looking towards the structure. And R0 and RD account are the losses. R0 is basically the, you can say, ohmic loss due to the metal, and RD is the dielectric losses due to the spacer. And the impedance is calculated by applying the simple formula of the parallel combination, and by putting the imaginary part of the impedance 0. When you calculate the Z from this value and put the imaginary part of the impedance as equals to 0, then you are able to calculate the resonant frequency by simple formulas of capacitance and inductance. And as you can see over here, the parameters vary influences on the absorption frequencies. As you can see, the resonant frequency is inversely proportional to the root of the permittivity and the length, not the width. So you can see over here, as you change the length, as the length decreases, you can see the absorption frequency increases. And as you can see the permittivity changes, the absorption level changes. So these are the two basic constitutive parameters. And these constitutive parameters, the researcher is able to find only with the help of the equivalent circuit modeling. And so that is the another way of thinking. That is the seventh rule, you can say. Means when you apply the touch uh, uh, equivalent circuit modeling on specifically on the absorbers, you please, I'll suggest you to please focus on the those parameters as similar things I have shown you in the wide stop and frequency selective circuits, in which case I have uh, discussed about the calculation of the peak of frequency. So in that, if somebody is saying, well, it is the direction of the electric field, please see over here, this is the direction of the electric field. This is the direction of the electric field over here. That is parallel to the wire. That is, so in that you can see over, so it is very much necessary, as I have stressed you in FSS case also, that it will be better while designing the equivalent circuit that you are able to find out what are the basic parameters on which the your actual absorption level or transmission level or reflection level depends. So if you are able to find out those parameters, then you are able to analyze the circuit very well. That is the, you can see over here, these are the basic two parameters on which the absorption frequency depends. Not only the absorption frequency, but absorption level is. So next we move towards the current scenario of the mechanical circuit modeling in Metamaterial. A very nice work comes from the IIT Kanpur, that the couple, if you see, it is simple square root. That is designed on the grounded dielectric circuit. Although we have also discussed the equivalent circuit modeling of the square loop, but that is in FSS, not in metamaterial absorbers. So if it is a metamaterial, grounded substrate. So the researcher has studied about the coupling effect. Uh, Coupling effect in the nearby, in between the adjacent unit cells, based on the coupled line theory. And even an odd mode analysis has been done. You can see in this diagram, when the wave incident on the such structures, then the surface current starts propagating. And where the surface currents in the adjacent cells are in same direction, you can see over here, when they are in same direction, that is here basically even mode. When the surface currents are in opposite direction, that should be in odd mode. And that direction you can see with the help of the field distribution or surface current distribution in your software tools. And by using these or observing these surface current distributions, you can this coupled line theory can be. And this coupled line theory is applied to actually calculate the value of the impedance and the of the FSS. And by using this value, the complete surface impedance of the absorber is able to, the researcher is able to calculate. So in this way, that is the another way of predicting the or other way of retrieving the parameters of the uh, parameter. And this kind of work comes out because there are many circuit models based on lumped circuit theory uh, has already been used to drive the element values, but they generally fails to explain the coupling effect between the neighboring periodic structure. So this comes out to be the first work, which comes in 2015, that if we consider this coupling effect as well, so the complete equivalent circuit changes. So that is, you can say, eighth rule, that it is not only fixed that you are going for the standard rules of the making the equivalent circuit. If you start from the basics, if you go for the basics, then you will definitely able to improve the existing theory of the equivalent circuit model. And here you can see this C with a substrate C, that is the coupling capacitance due to the periodic structure, that is counted in the equivalent circuit model. And the even mode coupling provides the vertical coupling only, whereas the odd mode coupling in this case produces both vertical and horizontal coupling in this case. And in this case, CFSS represents the and RFSS, LFSS represents the as usual standard values of the FSS parameters, but the additional thing that is considered over here is coupling clusters. So that is another way of thinking of designing the equivalent circuit model. Now, at last, I'm going to show you about the commonly used RF tools. I'm suggesting you that you can use to draw the your structures and for equivalent circuit modeling. I personally refer you about the advanced design system ADS and the soft designer in which you can design your equivalent circuit and compare the simulated and your equivalent responses accord. And now I'll conclude my session and giving you with some thumb rules. As we have discussed on the basis of the operational regions that for non-resonant elements like wire grid, strip, and patches, equivalent circuit is capacitive. That is the thumb rules that you can directly apply. And similarly, for single resonant type, it is a series LC. For double resonant structure, for multi-resonant, and for different multi-resonant structures. These are basic thumb rules you can take care while designing the circuit. And the another rules basically, you can see the agreement between the approximated and full wave responses is good if the FSS productivity is smaller than half wave, and it is homogeneity condition. And this averaged model works properly in quasi-static regime, but as frequency increases, this average technique model really fails. And the accuracy of the average capacitances and inductances can be improved further by using first order retrieval method. And if you want to operate your FSS within the resonant zone and getting the propagation, then multi-mode approach will be a better solution. And then mode coupling theory can be a better option to drive the equivalent circuit model. So with this, I'm very thankful to you for listening me. If you have any queries, happy to answer.
Okay, thank you, Dr. Deepak Sood. You have
Thank you, sir.
presented so nicely, and I think all the students might have get their answers. Now, if there are some questions, you can take the questions from the chat box because you have taken most of the questions from the chat box earlier also.
Yes, sir. Yes, sir. I'm trying to do it parallelly so that.
Sir, excuse me. Show me the references once again.
Okay, sir.
Thank you, sir. Thanks a lot.
Thank you, sir. Any questions?
Yes, sir. I think some of the chat box are remaining. Some questions in the chat box are remaining.
Hello.
Question is that, sir, for any FSS structure in the meter, they find the value of the circuit, and then according to circuit they find the reflection coefficient. Okay, and that reflection coefficient is curve fitted by the full wave simulation, and then they extract the L and RC values. My question is that, in many they draw the circuit, means LC component, and from that component they find the reflection, means impedance of that structure with respect to free space, and then from that formula they curve fitting through full wave simulations and find the value of RL and C component. My question is that if full wave simulation is wrong, our extracting parameter is also will be wrong. Then what is the benefit of the RLC component? Means they compare the two return loss, full wave simulation and one from the circuit formula. Compare and then by curve fitting they extract RLC value. So my question is that if the full wave simulation is wrong, like in HFSS, then the value which is obtained from the curve fitting formula is also be wrong. So what is the utility of such type of extracting the RLC component?
Sir, actually, in this case, the answer of your question is basically the what is the viewpoint of your observation. For example, if the structure is drawn and the equivalent circuit is mainly drawn for the normal incidence of the wave, please listen very carefully. And most of the structures, most of the equivalent circuit which is drawn are generally for the normal incidence, and they are also valid for the other oblique incidences if the structure is symmetrical. But if the structure is not symmetrical and the equivalent circuit is drawn, then it also works fine with the equivalent circuit. It also gives you the accurate results for the equivalent circuit as well. That's why when full wave simulation is done, then generally the reflection coefficient graph and the simulated reflection coefficient graph and the full wave and the equivalent circuit graph comes out to be same. But if it is tested for the oblique incident, then it comes out to be failure one. So the answer of your query is basically generally the equivalent circuit which are generally given in the research papers, you have to see, or you have to view in towards the perspective of the scenario that they are retrieving through the curve fitting, or they are retrieving through the some full wave simulations values, that if the designed structure is verified from 2, 3, or 4 values, then definitely it is going to be okay. Otherwise, it's going to be wrong if, let's say, you're saying in HFSS or in some other tool, if it not comes out, then you have to verify for what parameters, what constitutive parameters these provide. Are you getting my? Are you satisfied with my answer?
Yes, sir. Yes, sir.
Okay, sir. There
And
are
so
some
which tool is
questions in the
used
chat.
for curve, sir?
Sir, actually, curve fitting, you can use MATLAB as well. Curve fitting is nothing but that is you have to find out the parameters by studying the different, you have to study the effects or the parameters on the structure. And you have to observe that what are the key parameters on which the absorption or on which the transmission or reflection response depends. And by changing those values, you have to develop the equation by your own. Although there are softwares you can use MATLAB for curve fitting, no problem is there. Or in
Thank
some
you, sir.
HFSS is also you can write the equation in HFSS also and do the curve fitting as well.
Sir, now there are some questions on the chat box also. Is equivalent circuit generation by curve fitting is valid technique?
Sir, please repeat, sir.
Is equivalent circuit generation by curve fitting is valid technique?
Always, not always. Equivalent circuit technique using curve fitting, you have to actually, I should say it is, you have to judge by your designed structure, that for what purpose you are using. As you can see in my structure, I have calculated the first peak by the normal process, normal equivalent circuit modeling. And for the second peak, I have to go for the curve fitting, not for the first peak. So you have to judge it for what purpose you are using. In general, in most of the cases, it's okay.
So next question is, for a symmetric structure, symmetric equivalent circuit is necessary?
For what?
For symmetric structure, symmetric equivalent circuit is necessary?
For symmetric structure?
Yeah.
Symmetric structure, I think that symmetric structure is generally designed to make the structure polarization insensitive. Symmetricity plays a key role in polarization insensitivity. So I think the question is, when you design a structure, so please, if it will be better if you make it symmetric. So it works for all the polarization angles.
Okay, so next question is how to accommodate the absorption level above 90% when we are limited with substrate thickness and less permittivity and loss tangent values.
Less permittivity and substrate thickness. How to okay.
How to accommodate the absorption level below 90% when the limited with when we are limited with the substrate thickness and less permeability and less loss tangent value.
Okay, so in that case, what I suggest, it all depends upon the structure you design. Sometimes if you make your structure quite resonant or increase depending on the quality factor, as you see, the quality factor depends upon the inductance and capacitance of these design structures. So if you limit the permittivity, if you limit the thickness, all the things, then all the focus of your focus will comes out to be on the your design structure. You make your structure more resonant, increase the quality factor of the structure, so that it will gives you the above 90% absorption.
Okay, so next question is, if for DSL, if we put a connector in between two square loop in one side, then should we dismiss the capacitive effect of gap between two square loop?
So please repeat the question.
If for DSL, if we put a connector in between square loop in one side, then should we dismiss the capacitive effect of gap between two square loop?
So if you put the connector in between the two loops, the first thing that I want to show you, capacitance still plays a role, no doubt. Capacitance should be there. But you will make your structure, definitely it will be not polarization stable. It will not be polarization stable, but if you connect them two in double square loop, first of all, why you want to connect them? Are you to increase the coupling, first of all? If you increase the coupling, that means you want to increase the bandwidth. If you increase the
Hello,
bandwidth,
sir.
definitely.
Hello, sir.
Yeah. Yeah.
It is for whenever for active FSS. If we put the pin diode in between two loops, okay. So then whenever it is off mode, then capacitive effect will be there. But when it is on mode, then it will be act like a connector. And the pin diode is loaded in one side. That is there are four sides of this loop. Okay.
You are making a basically you are making a reconfigurable design basically.
Yes, sir. So if we put a pin diode in between the gap of these two square loops, whenever it is in on mode, in making the equivalent circuit model, so I have to design the pin diode model of its on mode in there. The other side, the gap is there. Okay. So for this other side, the capacitive effect should be implemented in the ECM model. Because I am I am asking this question because in the on mode, the current is from the outer square loop to inward square loop. The connection has been made.
Sir, in this case, firstly, maybe it will be better if I able to see the structure. But in that case, I know that the current will be different. In that case, you have to find out the correct placement of the active component while you are connecting the diode. And I have seen actually, not a single diode is able to give you the reconfiguration. Please check in your structure. As per my thought, you have to apply either 2 or 4 diodes if you are talking about to interconnect the two square loops.
No, sir. I have designed that using the 2 diodes in a single unit cell. Okay, and the design has been made in such a way that it is a polarization insensitive.
Okay. So if you are you are using 2 diodes, no, sir. You are not using a single diode. So naturally, if it is an off case, then when it is off, then capacitance comes out. Capacitance will play its role. When it under the on state of the diode, when both the diodes are on, that it is a complete one single resonant structure in that case.
Okay. Thank you, sir.
Okay, sir. The next question is it possible to make a metamaterial independent of frequency?
Sir, please repeat. Yes.
Is it possible to make a metamaterial independent of frequency?
Sir, yes, it's possible, first of all. Because if we are able to make a frequency independent antenna, then definitely we are able to make a frequency independent metamaterial based antenna. It is possible. And it
So
should be
next
angle
question.
dependent. Angle dependent. Yes.
Okay. So next question is, for a cross-section polarization converter, how can I generate the equivalent circuit model?
How
can I generate an equivalent circuit model?
For a cross polarization converter?
Yeah.
Sir, as you know,
Sir,
that while we are
C is also written. So one thing also written, for this I have a co-polarization reflection coefficient and a cross-polarization reflection coefficient. How to include both?
measure the co-polarization actually. Let's say if we talk about the measurement, then the orientation of both the antennas should be in the same plane. But when we measure the cross polarization, both the antennas should be 90 degrees to each other, as everybody knows. So if you are using a co-polarization cross polarization converter, then how the equivalent circuit changed, how the equivalent circuit can be modeled for a cross polarization converter. I think so. For change in polarization, with the help of the change in polarization, equivalent circuit modeling, you have to use a switch, basically. Active component you have to use in that case while designing an equivalent circuit. So when the polarization change, one section of the circuit will activate it, and for the different polarization, another section will be activated. So I suggest to use some active component in the equivalent circuit of the design, so that the switching of the polarization can also be considered in the equivalent circuit. Otherwise, in measurement, that only used for the reception, there is no need. But if you particularly talk about the equivalent circuit modeling, then you have to join the two sections in such a way that you have to use the active component in your equivalent.
Okay, sir. Next question is, why the bandwidth increase if we connect a square loop and a Jerusalem cross element together in a single unit cell?
Sir, is my screen is sharing, sir?
Yeah, sir. It's sharing.
So the answer of this question is in my. If the participant can see that this is one of the transmission peak, that is at the one frequency, and and for the Jerusalem it is at the different frequency. When both the structures combined with their optimized dimensions, then definitely the combination of the peak comes out, and you will get the higher band. That is the basic idea. Generally, if the bandwidth increases, so it is the idea behind it, and that happens actually in the design.
Okay, sir. Next
Another question.
How double negative property of metamaterial are used for application of absorbers?
Double negative property can be used for the metamaterial absorbers.
Yeah. Yeah.
Sir, double negative means basically refractive index is going to be negative, na? So
index and is going to negative.
refractive index is going to be negative. So when refractive index going to be negative, that can be used as we have seen in perfect lens. That can be used in perfect lens, but in case of, as he said about absorption, for double negative. So for a narrow band frequency, it can happen. It can happen for a single frequency as well, that you will get the absorption of a single frequency. But for the if the refractive index get negative and you want to absorb it, so in that case, I think there is a surface which is called partial reflecting surface. So in that case, the partial reflecting surface is a kind of surface which can absorb something and reflect something. So that can be designed using that.
Okay, and so last question for the day is how to design equivalent circuit that can define metamaterial property. Means that is similar to the previous question.
Sir, so that can be. Sorry, please repeat the question.
How to design equivalent circuit that define metamaterial property.
So that is the same question. That is the same.
Yeah,
That is
that's
the
why
same question. That is the same question. Like,
yeah,
so,
questions are coming. I will compile it and send to you because we are just ahead in the time.
no problem, sir.
Okay, sir. Okay, thank you, sir, for such a nice session. And you have covered means from FSS to absorbers. You have told about the different techniques, multi-mode approach, generic FSS system. You have told about the how to make the equivalent circuits of different elements, loops, Jerusalem cross, combination of elements. Also, you have gone through the modeling of absorbers. I think the research scholars have got benefited from your lecture to make how to make the equivalent circuits from there. Okay, I thank you, sir, on behalf of IEEE Rajasthan Substation, APS chapter, Government Women Engineering College, Ajmer, and MNIT Jaipur.
Thank you very much, sir. I am very thankful to all the IEEE Rajasthan subsection as well as IEEE APS chapter Jaipur, and to the principal, Dr. J.K. Digwal, for giving me opportunity to present to discuss my work. Thank you very much. Thank you.
Okay, thank you, sir. Okay, participant, again in the next session, which is of Dr. Raghavendra Chaudhary from IIT Dhanbad. Okay, thank you, Deepak, sir, once again.
Thank you, sir. Can I stop my, sir?
Yes,
Can I
sure.
stop sharing, sir?
Yeah, sure.
Thank you, sir.
Okay,
Thank you, sir.
you.
Thank you.